Okay, so where we had left off was I had introduced the idea of independent events. Two events are independent if the occurrence of one event does not affect the probability of another. So if you're given event A, that really doesn't affect the probability of event B had you been given that information. We talked about the multiplication rule for independent events, and the general rule was this guy here, okay? Now, one of the things that we'll have to do when we're reading these problems is we'll have to be aware if we have independent events. Just like in the case with mutually exclusive events, that's not something that they'll tell us directly in the problem. That's going to be something that we'll have to figure out on our own. If two events are independent and you're selecting multiple items, to find the probability of A and B, you're just going to simply take the probability of A times the probability of B. Now you can only use this formula if A and B are independent. If A and B are not independent, then you need to make sure that you're using the general formula. Now if you compare these two formulas, all I've done is replace the probability of B given A with the probability of B. The reason is because, again, just because we're given event A, that doesn't matter. If we find the probability of B, we end up getting the same result. There's a note below that. For some of the problems, we're going to need to work with probabilities involving the word at least one. These probabilities are usually going to be determined by using the complement rule. Let's take a look at problem 34. The probability that a randomly selected 40-year-old female will live to be 41 years old is 0.99855, according to a statistics report there. In part A, what is the probability that two randomly selected 40-year-old females will live to be 41 years old? Okay, because multiple females are being selected, we would know that this is going to be a multiplication rule situation. Now, just because one female lives to be 41, that really doesn't affect another female living to be 41. So along with using the multiplication rule, we would also want to recognize that we have independent events going on in this problem. What that means to us here is that the probability is not going to change from person to person. So there's a 0.99855 probability that one female lives to be 41. We need two females to live to be 41, so I would just simply multiply by that same number again, and I get roughly 0.9971. So there's roughly about a 99.71% chance that both would live to be 41. Part B, what is the probability that 5 randomly selected 40-year-old females will live to be 41? Well, this is going to be a similar deal here. You have multiple women selected, and so you're using the multiplication rule. Again, we would have independent events. Just because one female lives to be 41, that has no effect on another female living to be 41. So the probability is, again, not going to change from person to person. We need 5 females to live to be 41, so all I would do is just simply take the probability that was given and raise that to the 5th power. And it looks like there's a roughly about a 99.28% chance that all 5 would live to be 41. Part C, what is the probability that at least one of the 5 will not live to be 41? Okay, so I have that written here. Now, at least one means one or more. So that could mean that 1 could not live to be 41, or 2 could not live to be 41, or 3 could not live to be 41, or 4 could not live to be 41, or maybe all 5 don't live to be 41. Rather than computing 5 individual probabilities and then adding them, there's going to be a faster way to do this problem, and that is to use the complement rule. So remember, the complement rule says to take 1 minus the probability of the complement of the event. The opposite of at least 1 would be none. At least 1 means 1 or more, and so the opposite of 1 or more would be to have less than 1, and if you have less than 1, you have nothing. So I'm looking at 1 minus the probability that none will not live to be 41. Now, if none of these 5 women will not live to be 41, that means that all 5 will live to be 41. Which means rather than having a double negative in the wording here, let's rewrite it so that it's more clear. And now we've already found that probability in part B, so I guess to get the answer to part C, I would just simply subtract that number from 1. That was a rounded decimal, so of course I'd want to use the approximation sign. There is roughly about a 0.72% chance that at least one of the 5 would not live to be 41. Okay, that would be unusual since the probability is very small. It's likely that all 5 would live to be 41 is what we would take away from that. Now, as a note, just if I were to have calculated 5 individual probabilities and then add them together, I actually would get the same result here. It's just I'm taking way too long to do the calculation like that. So in general, it's going to be quicker to use the complement rule in the case of where at least one is keywords in the problem. Okay, problem 35 is another example. The packaging of an EPT pregnancy test states that the test is 99% accurate at detecting typical pregnancy hormone levels. Assume that the probability that a test will correctly identify a pregnancy is 0.99 if it's 99% accurate, and that 12 randomly selected pregnant women are given this test. Okay, part A, what is the probability that all 12 tests will be positive? Well, since we're selecting multiple pregnancy tests, we would be using the multiplication rule. Also, just because one test correctly identifies positive, that doesn't automatically mean that the next test will correctly identify positive. So we would also want to be aware that we have independent events going on in this situation. Therefore, the probability is not going to change from test to test. So I would just simply take the 0.99 and multiply that number by itself 12 times, or raise that to the 12th power, same thing, and I get 0.8864 as my answer there. Part B, what is the probability that at least one test will not be positive? Okay, so at least one, again, means one or more. So that could mean that one test, and by the way, if it's not positive, it's negative. So one test could be negative, or 2 tests could be negative, or 3 could be negative, right down the line. Rather than computing 12 individual probabilities, let's again use the complement rule since it'll be quicker. The opposite of at least one is none, and 1 minus the probability that none test negative is what I'm looking at next. Now, if none of these will test negative, all 12 are going to be positive then. So again, to avoid a double negative, let me rewrite the wording here. And I've already found that probability in part A. So to get the answer to part B, I would just simply subtract that number from 1, and it looks like there's roughly about an 11.36% chance that at least one will not be positive. Okay, problem 36 is another one. Among Americans who consider themselves auto racing fans, 59% identify NASCAR stock cars as their favorite type of racing. Suppose that 4 auto racing fans are randomly selected. Part A, what is the probability that all 4 will identify NASCAR stock cars as their favorite type of racing? Okay, so because 4 fans are selected, we'd be using the multiplication rule. Just because somebody likes NASCAR, that doesn't automatically mean that the next racing fan would like NASCAR. And so, along with using the multiplication rule, we would also want to be aware of the fact that we have independent events going on. So, the probability is not going to change from person to person. I need 4 people liking NASCAR, so I would just simply raise 0.59 to the 4th power, and it looks like there's roughly about a 12.12% chance that all 4 are going to like NASCAR. Okay, now what this tells me is, since this is a fairly low probability, is that at least one is probably not going to like NASCAR. Okay, and that brings me to part B of this. Part B, what is the probability that at least one will not identify NASCAR stock cars as his or her favorite type of racing? Okay, well, here's those words, at least one, again, so I'd want to be using the complement rule. The opposite of at least one is none. And I'm looking at 1 minus the probability that we have no non-NASCAR fans. Well, if we have no non-NASCAR fans, that would mean that all 4 are NASCAR fans, which I've already found that probability in part A. So to get the answer to part B, I would just simply subtract that number from 1, and it looks like there's roughly about an 87.88% chance that at least one person is not going to like NASCAR. Part C, what is the probability that none will identify NASCAR stock cars as their favorite type of racing? Okay, they told us in the problem that 59% of the racing population likes NASCAR, so therefore 41% of the racing population would not like NASCAR. We need 4 people not to like NASCAR, and by the way, just because someone does not like NASCAR, that has no effect over another person not liking NASCAR, which means that this is going to be another multiplication rule with independent events going on. And again, note that they're not telling me that I have independent events, right? That's something I got to think about on my own in the problem. 0.41 to the 4th is roughly 0.0283. That's a very low probability, less than a 3% chance that none of these 4 are going to like NASCAR. So what I could take away from that is I could say, okay, it looks like at least one is going to like NASCAR. Okay, and that brings me to part D. What is the probability that at least one will identify NASCAR stock cars as his or her favorite type of racing? At least one means one or more. So again, let's use the complement rule. The opposite of at least one is none. The probability that none like NASCAR, we've already found that. And looks like if I subtract that number from 1, I get roughly 0.9717. And so there would be roughly about a 97.17% chance that at least one is going to like NASCAR. Okay, since it's pretty unlikely that all 4 would not like NASCAR. And we'll stop right there.